This is a series of videos that tell the story of how my father and I came up with the four universal motions in physics. We highly recommend that you watch these videos in order. Enjoy. Back in 2015, my father and I came up with particle models for light, gravity, magnetism, and electricity. Back then, we called it the particle model. I then started to look at each particle individually, and when I did, I came up with a conclusion that I didn't want to believe. I took the idea to my father to see what he thought. It turned out to be perhaps the biggest discovery we had ever made. So, Dad, you remember that time?
It was an exciting time at the beginning.
Yeah.
Things exploded after that.
Yeah. I mean, it was really crazy. And of course, if you're just joining us, maybe this is the first video. This is a video we've made of, I think, 4 or 5 part series about how we came up with what we call the 4 universal motions. So if you look at it, our particle model at the time were these 4 motions. We didn't call them the 4 universal motions. We just called them a particle model for each of these phenomena in physics: gravity, electricity, light, and magnetism. We called it a gravitic field, an electric field, a luminic field, or in a magnetic field, all these things. And the gravitic motion was random motion, and that governs everything. From that, all the organization of the universe comes at all different levels. You can have this at all the infinite levels of the universe. We had also the luminic motion, which is light, which my father came up with, which was particles traveling together in waves at the same speed, not one particle. And these particles comes in waves, just like bombers. Magnetic motion came from Lionel Deneu's underwater experiment, which showed us that orbiting particles, when they come together, when they're in the opposite direction, they attract. If they're in the same direction, they tend to hit, and they move away from each other. And then electric motion is simply a one-way direction of those same any type of particles. To us at this time, they were just particles, and you'd have particles for gravity, graviton, you'd have the electron for electricity, you'd have the photon for light, and then we would have a magneton. If that was existing, we would make it up. So once we got all of these particles, I said, okay, let's take a look at each of the particles individually. And I just wanted to see, okay, what do we have? So what I started to look at was, first of all, just the speed. How fast do these particles go? And of course, light travels at the speed of light. I thought, okay, well, wait a minute. Gravity also travels at the speed of light. And that's according to mainstream science. But it's also according to several Chinese studies in the late 1990s and early 2000s. And I learned that from my dad. There was a total solar eclipse in 2001. Chinese scientists conducted this experiment to investigate the speed of gravity. They were building on their work from 1997, an eclipse in China, and they used ultra-sensitive gravimeters or gravimeters to detect minute fluctuations in the Earth's gravitational field during the brief moments of totality. Their hypothesis was based on the idea that if gravity is mediated by particles, that's interesting to what we've been saying, then the moon might partially shield Earth from the sun's gravitational pull during the eclipse, producing a measurable dip. Now, of course, it's funny they call it pull, Dad, here, but obviously it would be a push. If it's a particle, it's pushing us. The team recorded subtle anomalies of gravitational acceleration, which they later analyzed alongside Earth tide data for multiple eclipses. Their findings was published in Physical Review D, which is very well respected in mainstream physics, and it suggested that gravity propagates at the speed very close to light, between 0.93 and 1.05 times the speed of light. Of course, that's right around the speed of light. So yeah, it's been experimentally confirmed by these Chinese scientists. Next, I looked at electricity. I go, well, that's the speed of light. We can actually measure. You can do experiments in the lab. And it turns out that if you really look at electricity, it is known to travel at the speed of light. And so we have light, gravity, and electricity all traveling at the speed of light. So I go, okay, how about magnetism? You can't measure magnetism. So I thought to myself, where do we use magnetism? And we have some idea of speed. Well, in particle accelerators. Why? Well, particle accelerators, the idea is that you can use magnetic fields to accelerate a particle, well, how fast? To the speed of light. So I'm thinking, that must mean magnetism must travel at the speed of light. That means gravity, light, electricity, and magnetism all travel at the speed of light. So you really only have kind of two choices. And it's funny because I came to this conclusion very quickly. It's not like I spent weeks thinking about it and struggling upon this idea. So if there's really only two choices that you have. Something causes them all to move at the speed of light. And if you think about it, that isn't easy. How would that happen? Why would that be? I mean, you'd have different particles, probably with lots of different properties, and they would all have to be moved at the speed of light. And if you even think of it mechanically, if one's bigger than the other, one's heavier than the other, there's other different kinds of, how would that happen? That'd be very complicated. And the only other conclusion is kind of shocking in that they all were the same particle. When this hit me, I thought to myself, man, this is too crazy. How could it be that gravity, light, electricity, and magnetism are all the same particle? Is that even possible? So what did I do? I went to my dad, who's sitting there with bated breath, and I said, Dad, I came to you, right? I did. I don't even remember I think you were still at the apartment in Long Beach, California. And I walked into your office and I said, hey, Dad, so Dad, do you remember me coming to your office and saying, Dad, I've got this crazy conclusion. They all travel at the speed of light. Could they be the same particle? Do you remember that?
Yes, I do. The thought that I had was that if you have what you might consider to be different particles all moving at speed c through the same space, or it's open space or some sort of gaseous space, but they're all moving through the same homogeneous space and they're all moving at speed c, then it would seem like even the simple mechanics of that is the ability to accelerate or slow down or turn. So if it's all these, what you might have considered different particles are moving at the same speed through the same medium, then they're probably the same particle because they're all subject to the same drag, acceleration, and turning forces. So yeah, it seemed to me that it makes sense that they're the same particle. If one's much bigger and one's smaller, colors probably don't matter, but shape, one's square, one's round, one's pointed, they could all move differently. So not only are they would be the same particle, but in the sense that they're the same shape, moving through the same medium, moving at speed c is the same particle.
For some reason, which really kind of shocked me, is that you didn't kind of think about it. Wait, Dave, there's gravitons and there are electrons. Electrons have charge and blah, 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 blah. That didn't seem to bother you.
No, because I focused on the issue of the speed going through. You asked me that question. I was focused on that. Yeah, you can back up and repeat what I just said a few minutes ago and start analyzing it in more detail.
So the other thing too is I think at that time, because, for instance, like with the electron, we already said to ourselves, there's no such thing as charge. We were just thinking of the particles as stripped down, no attributes. As Alexander Unziger says, they're arbitrary packages with arbitrary attributes. That's what kind of particle physics has become. And so we were looking at real things that we were trying to say. And these are real physical particles, and they're moving in these ways. And this is what you call them when they move in those ways. And we just we couldn't put a magical thing upon it. The only way something changes is you have a collision. You have a force that moves it. Two things hit each other, and that changes something in the universe. So we didn't have that. I don't think you're in the mindset at that time to think, oh, he's talking about these four things, and I'm thinking about mainstream physics and what mainstream physicists will say about that. Now, that's what I was kind of thinking when I came to you. I was thinking, this is crazy. I mean, whoever would have thought that these particles are the same? There's got to be millions of people on the planet who already knew that three of them travel at the same speed, right? No one came up with the idea that these could be the same thing. And I think part of it was because they were so stuck in their little world of each one of these particles that they were just tied to something that said that would be impossible. What do you think that the mainstream scientists, if we told them they were all the same particles, what do you think they would say?
They'd probably stop and say, well, wait a minute. if they're the same particle. I'm now be a little bit critical here. Then these particles have to be coming from almost the same place, and wherever that is.
Yeah, I think they would just be very argumentative because each one of these particles has their own world, and to think that they would be all the same particle, especially the electron with charge, they would just, I don't think they could ever accept that. Once I came to you with the idea that they're all the same particle, and you go, yeah, that's the logical conclusion. It really, looking forward, really solved a lot of problems that in physics were kind of magical, or they just had no solution for that. And here are some of this. Not so crazy. Electricity turns into light. You have electrical current. It goes into a light emitting diode, and light comes out of it. That's explained in mainstream physics as an electron changes in an energy level or a level and releases a photon. Yes?
Any particle hitting an atom, if it knocks the electron to a higher energy level for some reason, which they don't say why this happens, I can see why it got pushed up, but it says, well, that's not its natural place. So somehow it magically comes back down to its natural level. And as a consequence, that has to release some energy. And that energy, we're now going to turn energy into a photon. That's magic.
Yeah, it is. And it's funny because the energy is a concept. It's not real. And that's one thing that people, if you are a person listening this first time and you think energy is something real, hold it and give me a handful of energy. Energy is a very good calculation we use in physics to calculate a translation of type of movement or work that we have from one system to another. But energy is their way out. They just say, oh, it's energy, and then energy and light, or everything's energy. So there you go. The other one is really interesting, is wireless charging. That's another one where you have current in a wire, it's moving around electrons, and that current induces a current in another wire through the air. And yet they don't talk in physics at all about whether or not there's some transfer. When a person sets their phone on a wireless charger, they're really thinking there's electricity there and it's getting into my phone. Now, if you think about it, that would be electrons being transferred, but that's not the way mainstream physics talks about it, right?
No, they use that exact word you have in quote. It induces the movement. But what in the world is induces? That almost sounds like a force. Which one of the forces involved in inducing motion in another wire? So why was it stated so vaguely? Why can't we pin this down to something specific and give it a true physical meaning as to how the motion in one causes the motion in the other? So induces isn't an answer.
The last thing is magnetic fields, which is kind of related, right? Electricity, it creates these magnetic fields, and magnetic fields and current and light have these inexplicable relationships, right? Light is electromagnetic waves. So there's already kind of the words are there that electricity and magnetism are somehow related in this perpendicular. I promise I'm not putting the perpendicular graph up there because that triggers my father and I. But the idea that you have this electricity and it creates magnetic fields. Again, how? Why? In your wireless charger, there's a magnetic field there. Is that magnetic field's what's inducing the electrons to move through the air? Because yeah, we know that magnetism, everyone understands, anybody can do an experiment, that magnetism is in the air. It's going through the air. That's a real thing in the universe. Everything is something real. There's no force that my father and I believe, and there are other scientists who also think the same. There's no force without some physical thing, physical movement. So that's another crazy thing, that you have electricity going through a wire, and a magnetic field is induced, right? I guess would they say that?
Yes.
Yes. So there's that magical word. And if you look at electricity and magnetism and light are all the same particle, electricity can turn into light. All it's doing is modulating and sending out these particles that are electricity and light and gravity and magnetism in waves. So that's all that's happening. You have an explanation. Wireless charging. Yeah, the electrons go through the wire. They get into kind of a spiral motion, which creates these loops, which are in the air. And those things go and they're captured by your phone. That's the other thing, Dad. If you think about it, it's crazy to think that you have a phone, and if you told people that it induces the current in the phone, where's the electrons coming from? Are they somewhere else in your phone? Did they go into your phone case and then your charger's saying, okay, go run into the battery now? Even if you believe in the magical induce that all of a sudden electrons are moving, where are they coming from? So, I mean, it's crazy to think that if you have your phone and you are putting it on a charger, that this induction, even if you believe in an induction, that's the way it works, this induces electrons to move in your phone. Where are they coming from? Basically, let's call it what it is. We don't even call it the electron. We just call it the G1 particle. This particle, which is the same particle, goes through a wire. It's moving through the wire, but it also spirals because of the copper atoms. It's going outside, kind of like orbiting. And those things are in the air, just like a magnetic field. And those get captured into your phone. It's pretty simple. Like I said, otherwise you have to think to yourself, well, they're sitting somewhere and now they're being induced and they're coming back into your, it makes no sense. So,
one of the things that people don't know about, or they understand, or they think they understand, that electrons stay in the wire. G1 particles stay in the wire and they don't jump out. That's not part of the mentality of what electricity is. So first thing here is you got to convince people that as the G1s going through the wire, it's possible that these G1s leave the wire and go around.
Right. And when people are going to ask, well, what's keeping them there? Well, what keeps and moves these particles for light, gravity, electricity, and magnetism, what keeps them moving and orbiting and all that is another gravity below it. And that's why we call G1 particles. Those are G1 particles at the level 1. There's another level below. And that's where you get the Coulomb effect, where they say, things, electrons orbit the nucleus. Well, if they're orbiting, we know what causes orbits: a gravitic field, random particles moving around a direction. So there's got to be another level below us, but that's a video and another story. So,
because I was ready to really jump in there, because to me, that was exciting to see that. To come to that conclusion when I made the drawing and I saw it.
Yeah, so you're going to have to stay tuned to our next. Exactly. Thanks, you guys, for tuning in. Remember, trying to tell you the story about how we came up with the 4 universal motions, which actually happen at all the levels of the universe, infinite levels, from infinitely up and infinitely down. And what kind of animal is infinitely up and down, Dad? It's turtles all the way up and turtles all the way down. All right, guys. See you in our next video.